First of all, thanks to the organizers for inviting us to give a talk in Swampland Seminars. I forgot to mention the references. So this talk is based on a paper we put in February with my collaborator Fotis Farakos, and a more recent one. It's mostly based on that with Tim Rasa, Zheng Miao, and Mutuzami Rajaguru. And I'll be talking about T-dualities and three-dimensional scale-separated AdS vacuum in type 1. Okay, so I will do the introduction. I will give you motivation for why we are doing what we are doing, why we're choosing to work to compactify down to 3 dimensions. I will tell you about the recent progress during the 5 years, what we have achieved in this scale separation program, and the issues that we have maybe not resolved yet, and they're long-standing since 2005. And then I will talk about these scale separated solutions, the AdS3 solutions in massive type 2A on Joyce manifolds, and then Mutu will talk about the dual theories of those constructions. Let me start with a very general introduction, and just to remind you that the goal, at least of my research, is to try to find effective field theories which possess the characteristics that our universe has. For example, we would like to find a mechanism and understand the mechanism that keeps the extra dimensions hidden, or we would like to stabilize the moduli. And once we construct this theory, we want to make sure that this is UV complete. Why we do constructions down to 3 dimensions? The reason is because the gravity behaves differently, and maybe things are easier, and we might get some insights for higher dimensional constructions. If, for example, you construct an AdS3 solution, it might be more possible to understand the CFT2 theory, since we have better understanding of CFT2. So one reason for sure is holography. We also want to understand, since 95 of the Fino projects on the string Fino projects are in 4 dimensions, we would like to see if we can successfully stabilize moduli also in 3 dimensions and find scale separation broadly in supergravity or in string theory. And of course, another reason is because we want to see what happens with the lower dimensional theories. I mean, like the 3D theories and the Swampland program. So the scales that I will be comparing in this talk, there are 2 scales that come from the compactification. Is of course the KK scale, and it's the vacuum expectation value, or the radius of the AdS, the external space that we have. Okay, so we'll be comparing actually the vacuum expectation value to the masses of the KK modes, and we want this parametrically to become small in order to hide the extra dimensions and achieve scale separation. Of course, our construction is not the first one. The first one was built with all those characteristics back in 2005, the so-called DGKT and CFI. It was constructed from a massive type 2A. And with smeared O planes, with Romance mass, H3 flux and F4 flux, which was like the unbounded flux. So tuning this unbounded flux and taking it to infinity, you could reach like a classical limit where you achieve scale separation and the theory is well controlled. What I will be talking about mostly in my part is this last bullet here, about integer conformal dual dimensions, which is a property that DGKT has. So when you try to find the CFT, some characteristics, to understand some characteristics of the CFT theory, you find that unexpectedly, maybe because through some complicated, some non-trivial formula, let's say, you get integer conformal dimensions. I will focus on that in my talk, and I will try to relate this to the tadpole cancellation and maybe to the resolution of the spaces that we have been working during the last year. Another important issue, I mean, this is like an issue, is the smeared sources. So when we smear the sources, actually we neglect back reaction. And this means that we cannot solve the 10-dimensional equations exactly. Um, and this is a problem. But during the last years, many groups have been trying to understand what's going on with the back reaction, even by performing like analytical numerical solutions, either by performing like some perturbative methods, and they solve including the warping second order kind of equations. And more recently, there are very nice arguments from Daniel Junghans that there is no actually intersection when you do the when you blow up like properly. There is no intersection. There is no like such a problem that people usually complain about. Uh, as I mentioned in the introduction, we would like also to see what happens, what is the status actually of scale-separated constructions into the swampland. Of course, the swampland sets constraints, and it tries to direct us and tell us which effective theories of gravity can arise from like a consistent UV completion, such as string theory. During the last years, uh, many groups have tried again to test the distance conjecture. And I think that roughly, let's say, scale-separated constructions, both in 4 dimensions and in 3 dimensions, they're doing well. More recent constructions, where they use the brain picture of the AdS vacuum, they find some inconsistencies. But still, we are trying to understand what's going on with these special vacua. And I think that they can. I'm not sure if those constructions apply actually, or they have been, or our constructions that we will present here, they have been tested to see what happens. Let me now tell you about the more recent developments on this program related to AdS scale-separated solutions. So from 2005 to 2020, actually, people have been working with DigiKT CFI, with the 4-dimensional scale-separated constructions. Till then, we had no clue about scale-separated constructions in type 2B. We had no clue about the possibility of performing like an M-theory uplift of DigiKT, actually. So 5 years ago, we constructed something similar to DigiKT in the sense that we start from massive type 2A with the same fluxes. We compactify, of course, in a different geometry, 7-dimensional geometry, G2 holonomy, and we get exactly the same properties as DigiKT. The difference is that initially we did it using a singular orbifold, and this will play an important role to what I want to say. So a couple of years ago, also people T-dualized DigiKT. They arrived to a type 2A theory, which is without the Romance mass. And they managed to find some indication and even like specify the internal space that that can lead us to an M-theory uplift. As I mentioned, in the 3 dimensions, people managed to find scale-separated solutions, which are not compactified on G2 holonomy, but with G2 structure, and those are very related to the type 1 construction that Modu will talk about. We found also other families of theories related to DigiKT and to these 3-dimensional models. We tried to see how broad we can find scale-separated setups in 10-dimensional supergravity by just treating the universal moduli of the theory. And it turns out that maybe it's achievable, maybe. Recently, people, okay, maybe not that recent, yeah, recently people have been also trying to construct scale separation in 2 dimensions, but if I remember well, those constructions do not include O-planes. So I think in the end, things do not really work as we want, but I'm aware that some groups right now, they're working on that. And most importantly, as I mentioned in the beginning, in DigiKT, people found out that when we calculate the conformal dimensions of the dual theory, they turn out to be integers, non-trivially. While for the singular AdS3 constructions that I will present, also this one and the Joyce orbifold, for the singular one, the conformal dimensions are not integers. All right. Why do I personally think that during the last years, maybe we have done some progress? Because the scope of the whole program is to understand whether scale separation can be realized in supergravity or in string theory. And I think that maybe we didn't achieve that, but we constructed, let's say, new directions, new paths to test that. Because we started from a massive type 2A, we T-dualized and we got like a type 1 theory. And one of the solutions of the type 1 theory actually turns out to be a heterotic SO2. And this is something that people can examine and they can understand better whether we can see we can actually study the worldsheet perspective easier compared to type 2 supergravities. All right, so let me start. Again, my focus will be this property of conformal dimensions, of integer conformal dimensions, and I will try to relate it to the tadpole cancellation. As I said in the beginning, the internal space is a G2. Is a G2 space. Is characterized by this tree form, the fundamental tree form, and it's dual. And the moduli, we will deal only with the bulk moduli. There are eight moduli in total, so it's the dilaton and the internal space deformations. They're represented by SI. The G2 colony has the following properties. Is Ricci flat, so phi is closed, psi is also closed. But in order to get analytic results, we have to be more specific on our constructions. That's why we will work with these so-called Joyce orbifolds, which are actually toroidal orbifolds, and they can be resolved. How they can be resolved? If you go, I mean, this is like those are the generators of the group of the orbifold group. You have like these three generators. You can also take combinations of them, and they all consist the orbifold group. So if you, for example, set these shifts to 0, you will get a singular orbifold with many fixed points. Let me show you what happens then. In our constructions, we have O2 planes. So when we require the orbifold image, actually, the combination, more or less, of the O2 involution and the toroidal involutions to be like a physical object, we generate O6 planes. We generate many O6 planes because we have many fixed points. If, however, we consider a Joyce orbifold as not a singular orbifold that can be resolved, okay, and we take into account those shifts that I showed you here, you get less fixed points. And in the end, instead of having like an O plane which wraps 7 directions, you have just an O plane which wraps like 3 directions, or you have like 3 O planes. Let me tell you that you have three O planes. All right, we compactify, we can perform like a dimensional reduction, we can compactify, we construct our 3-dimensional effective theory. We know the Keller potential for these G2 holonomic constructions, for the G2 constructions. We found the superpotential, so we can actually derive and work out the n equals 1 3-dimensional supergravity that we can get. And of course, it matches to the dimensional reduction. So now we have the superpotential. It consists of those 3 terms of 3 fluxes, the H3 flux, the F4 flux, and the Romance mass. And one can just plug in these fluxes and take into account the geometry and can minimize the superpotential and study the vacuum. All right. But before I go there, there is very crucial to understand what happens with the tadpole in the singular orbifold case. So in the main difference compared to DGKT is the following. In DGKT, we only have O6 planes. We don't have O2 planes. But here we need actually the O2 planes in order to get n equals 1 supergravity and to stabilize the moduli. If you go to the singular orbifold, you want, of course, to keep the F4 flux unbounded because this is the flux which controls the whole theory. And if you cancel here the charge of the smeared O2 plane with those fluxes here, they will get bounded. So a way to keep this unbounded is to engineer your fluxes such that they cancel out, the sum of them cancel out, they remain unbounded, therefore flux, this is the F4 quanta, remains unbounded, and then you cancel the O2 with D2 branes. If you do this, you're fine, you're probably fine, in the sense that you can find an AdS vacuum with the properties that we are looking for. It's scale separated, parametric scale separated, large volume, and weak coupling. But the conformal dimensions are not integers. All right, let's try actually to go back and see the Joyce manifold, which can be resolved. As I told you, this one, instead of 7 O6 planes, it has like only 3 O6 planes. And in order to cancel the tadpole, unfortunately, maybe here in this construction, we have to pick a different flux ansatz. Let me explain you why. Since I have 3 O6 planes, I can have like only 3 H3 fluxes, okay? And I can pick my F4 fluxes such that when they wedge with H3, their wedge vanishes. This means that we don't really have to tune the fluxes such that their sum cancels. They cancel geometrically, let's say, okay? And then you can cancel the O2 planes with D2 branes. However, if you just do this and you just keep only the first line of this flux ansatz, of course you will in the end you will get massless fields. So in order to save the situation, one has to go and engineer another way. We cannot put more H3 fluxes actually, but we can add like more F4 fluxes. And this line, it looks somehow non-trivial. So if we plug these flux ansatz inside the tadpole cancellation, and we can pick the fluxes such that they satisfy the tadpole cancellation, but they're engineered such they're again fine-tuned. We have chosen like signs and the coefficients in order to engineer these fine-tuning cancellation instead of having like a geometrical cancellation. Is this a problem? Let's see what happens when one does that. So we can plug these flux ansatz in the superpotential. We can extremize the superpotential, and we can actually stabilize the moduli in terms of fluxes. There are some fluxes which are unbounded here. There are some others which are bounded by this non-trivial cancellation that we used. Again, we pick these complicated flux ansatz in order to be able to stabilize the moduli. If we don't do this, we don't have enough fluxes actually to stabilize the moduli. So parametrically, not all of those fluxes matter. There are a few of them that matter. Actually, there are two fluxes: the calligraphic, sorry, let me see, the calligraphic G and the N flux, which matter. But parametrically, you can get small string coupling and large volume. The vacuum expectation value, of course, for large values of those unbounded fluxes becomes small. And then you can compare the vacuum expectation value to the masses of the KK modes. And you see that, I mean, of course, there are like some conditions which depend on the scaling of the fluxes, but you can achieve easily a scale separation. So those two scales decouple, and you can find a hierarchy of your fluxes in order to have a classical solution with scale separation. All right, how this non-trivial flux, this fine-tuning of fluxes affected the conformal dimensions? Let me show you. So we had 4 F4 fluxes that we were able actually to not to tune. So we were able to cancel this F4 wedge H3 term in the tadpole cancellation geometrically. And we get integer conformal dimensions when we do this. When, on the other hand, we tune the flux, okay, when we fix the signs in order to perform like the stabilization and the tadpole cancellation consistently, we find we find that the masses, so okay, so these are the eigenvalues of the Hessian, they depend non-trivially on those fluxes. But when you go to a parametric large limit for one of the fluxes, they all tend to become integers. There is a solution. There is a type 2b solution. It's listed in Vincent's paper, where actually this behavior is natural. You don't have to take this parametric limit in order to make the other four conformal dimensions integers. But we have not actually dualized this to type 2a to see what is the form of type 2a. And the question is, we started from a singular orbifold. All the conformal dimensions were non-integer numbers, and then we started somehow not resolving, but picking like shifts that can lead to a resolved orbifold. And we noticed that we started getting like integer conformal dimensions, a property similar to what a DGKT has. So we don't know whether this can actually tells us or can show us some direction to which resolution we should pick in order to get. I don't know if this is somehow related to scale separation. But that was a question that people have been trying to understand for like a couple of years, and I think that this is the result, that when you tune the fluxes in order to satisfy the tadpole cancellation, the conformal dimensions mess up. When you start using like shifts in your orbifold, then you get this property of the conformal dimensions. That's what I wanted to talk about. Now Mutu will continue with the T-dual theories of these setups. Let me stop sharing maybe or no. Shall I stop sharing or other
Yeah,
questions?
maybe I think you can stop sharing, Mutu
Okay.
can continue. If someone has an some question that wants to do now, can do it. Otherwise, general questions can be at the end.
Yeah, maybe I have a comment if I
Yeah.
So I think also why in some cases you get these integer conformal dimensions is that if you have a theory with certain fluxes, well, with certain non-zero fluxes, then it can happen that you can do a field redefinition. So you rescale your moduli by some fluxes and a power. And if you can do that such that the potential becomes an overall factor, including all of those fluxes, and then a function in terms of all of these rescaled moduli, which does not depend on any flux, then in the end, what this will tell you is that if you compare or if you compute the mass spectrum in terms of AdS units, then these will not depend on the fluxes. And in this case, I mean, it's already a bit easier maybe to get integer conformal dimensions. I mean, it's not guaranteed, of course. For instance, in AdS 5 plus S5, something similar happens. But it seems that this might be a requirement, or at least this, or at least, well, gives you, at least can give you it. Because indeed, if the potential depends on the fluxes, then you have additional parameters in the game. So if you cannot do rescaling, I mean, then it's probably a little bit more complicated, or will probably not happen. Yeah, these are just my 2 cents.
Yeah, and I just had a brief question. So with these interconformal dimensions, I mean, usually like in a CFT, if it's an interacting CFT, usually I only expect integer conformal dimensions for things like, conserved currents. So is there some sort of indication, in this construction that there's some extra, symmetries or something along these lines.
I think it's what Vincent said probably. I think it's what Vincent said, right? I have not
well,
thought
I was
about it this
asking more
way.
about like the CFT interpretation, not necessarily like how things
Yeah, we have not
conspire.
thought about it like this, to be honest.
Okay, all right, thanks.
But thanks for pointing this out. Yeah, thanks for pointing this out.
Yeah, Ethan, just to like follow up, I think Fiend has thought about it along these lines, but I think the picture is not clear yet, like what the exact conserved current is or what the symmetry is. Yeah, anyway. But I think that's the important question. That's the point, I think, from the CFT side.
Yeah, I was actually gonna follow up on that, right? Like there's this paper of Finn showing that you will have the conformal dimension whenever you have these symmetries with some space dependence. Have you thought whether this, I mean, you said that you see the difference when there's tuning of fluxes or not tuning. Is this related to this symmetry somehow?
I thought about it a bit. I haven't managed to make the connection. I also think in Fiend's paper for the 3D case, somehow this argument doesn't go through that easily.
Exactly, yes.
For the 3D solution.
For the 3D for a singular orbifold, there are some issues indeed in Finn's checks.
But this would be interesting to check for sure. I mean, we discussed with Finn a bit about this, and yeah. I think Thomas also has a question or comment.
Yeah, sorry. Related to this, there was a paper by the Madrid group a while ago where they observed that in the original Type 2A constructions for AdS4, there are discrete higher form symmetries, which of course should also exist in the CFT. And I was just wondering whether the difference between the examples in 3D that have integer conformal dimensions or not, whether it's also about having these discrete higher form symmetries or not, because we know when we don't have the integers, we also could not find the discrete higher form symmetries.
It's a great question. Actually, Finn asked me a similar question last week. The point is, before resolving, there are no axions in this setup, at least in the setup that we're working with. So at least in the toroidal orbifold picture, I wouldn't know how to see it, like to see what the discrete symmetry is. I think the analysis that you guys did, for example, with Finn and Miguel and Tim, for the cases where you don't find integer conformal dimensions, I think to run those arguments, I wouldn't know like for what objects to look for. But if one can resolve it, and I think people are working on this, we're also thinking about this, maybe this kind of question can be answered in the future.
Okay, thanks.
Okay, let's continue with the second part.
All right, let me stop sharing.
Okay. Perfect. All right, so let me also begin by joining George and thanking the organizers for giving us an opportunity to speak about our work. So let me put you through the painful process of sitting through a 2-minute recap of what George spoke about in case you disconnected in some way. Okay, sorry. Sorry, 1 second. I wasn't able to move slides. Okay. I hope that fixes it. Okay, yeah. All right. So just to recap, what George and friends did was, sorry, the same thing keeps happening. Okay. What George and friends did was start with massive type 2A. Can you see my next slide?
Before we could see that you change it, but then come back to the first.
Sorry, I don't know what's happening, but
It's okay.
Try to fix this quickly. Okay, this hopefully should work. Okay, finally. Sorry. Anyway, so just to recap, so George and friends started with massive type 2A, so type 2A with the Roman's mass parameter, compactified on a 7-dimensional manifold with G2 holonomy, included appropriate fluxes, and the claim was that they ended up with some 3-dimensional effective field theory. Of course, to justify this claim that you're working with the 3D lower dimensional effective field theory, you have to actually find scale separation for the vacua that you find. And the claim here is indeed that you can do this, that you can find AdS 3 vacua with scale separation, which is very similar to the DJKT CFI vacua. So here we're speaking about parametric scale separation, right? You have some free parameters that you can dial as you wish. All the scales in your theory depend on the free parameter, and you can separate the scale of the AdS vacuum from the internal dimension arbitrarily. Okay, fantastic. So just to remind you a bit more of the details, what we will speak about mostly today are toroidal orbifolds. So in particular, George already showed you a set of orbifolds that we're working with. And the defining feature of these manifolds with G2 holonomy is the existence of a fundamental 3 form and its dual 4 form. And all the metric deformations are captured in terms of moduli associated with this 3 form. So what's happening here is you take massive type 2A from 10 dimensions, compactify on a G2 holonomy manifold, which is flat, so there is no torsion. And you end up with some 3-dimensional theory with 4 real supercharges, right? And we would like to go to minimal supersymmetry, so we do an orientofold, and this takes us to 3D n equals 1 with 2 real supercharges. And one can play the usual game of trying to generate a scalar potential for these moduli, these universal moduli, by turning on fluxes. And this is a game that most of us here are familiar with. So you generate a potential which is controlled by the field space metric and the superpotential, which for the massive type 2A case, at least on a G2 holonomy manifold, was derived by George, Fortis, and Thomas about 5 years ago. And once you have the superpotential, you can go and ask what are the supersymmetric vacua of this theory, right? The story is very similar to the 4D case. You ask for critical points of the superpotential at which the superpotential itself is non-vanishing. So this guarantees you critical points of the scalar potential with a negative vacuum energy at the minimum, right? And this people have understood for a while now that you can construct in principle AdS vacua and other kinds of vacua in 3 dimensions. But I think one of the more important and new inputs from George and collaborators was that you can also get parametric scale separation in these constructions. And they have very interesting properties, some of them at least, like integer conformal dimensions and so on, that George just told you. But the question that I'd like to address in the remaining minutes of my talk is, can we move away from massive type 2A? There are several issues that people have brought up in massive type 2A, like the interplay of the Roman's mass and orientofold planes, whether we understand them and so on. So one can naturally ask, aren't there other supergravities where this nice property is allowed, or is this specific to massless type 2A? I think this is not a new question. People have asked this question many, many years ago, immediately after the DJKT CFI vacua appeared in the literature. For example, Banks and collaborators tried to ask, aren't there T-dualities that take you to massless 2A, where you can remove the Roman's mass parameter, and you can still keep this property of parametric scale separation. I think this was also investigated more in a follow-up paper by Dieter and collaborators. And the naive answer they found was that it seems you have ingredients, but you cannot satisfy flux quantization and moduli stabilization while maintaining this property of parametric scale separation. But more recently, Nicolo, Daniel, Vincent, Thomas, and Tim, many of whom are in the audience, pointed out that looking at the equations more carefully, that you do have a way to solve the equations in such a way that you have a scaling freedom. And there are different parametric limits you can take of the free parameters you have once you solve the equations, such that not only do you get scale separated solutions at weak coupling in massless type 2A, but that you also have a strong coupling family of solutions. And these permit a potential uplift to M theory. And there's been progress along these lines from Vincent, I should have mentioned this paper as well, to try to understand sort of the exact 7-dimensional background you need to go from M theory to the 4-dimensional scale separated vacua. The status in type 2B is slightly less clear. So people tried playing the same game. Tim and collaborators and Thomas and collaborators tried starting from Calabi-Yau or generalized SU3 structures and doing T-dualities to end up in type 2B. And the claim was that there were scale-separated solutions, but then Tim and Thomas and collaborators themselves pointed out there are some subtleties in these vacua. So, for example, in the limit where you seem to have scale separation, where the coupling goes to weak, the coupling becomes weak, the internal space volume is large, and the AdS space volume is parametrically larger. There are some cycles in this internal manifold that are becoming small. So these are not necessarily solutions that we would trust. But the main lesson I want you to take away from this, or the main lesson that I'm going to take away from these sets of work, is the fact that you can use T-duality as a sort of a guiding principle to identify what ingredients you need. So you don't need to take the T-duality too seriously. In principle, we are performing a T-duality to understand what sources and ingredients you need on the other side. But in principle, you could have started from there without starting from type 2A in the first place. I'll make this point again when I actually show you our results. But more recently, some progress has been made in understanding the story in type 2B in 3 dimensions. In four dimensions, the story is still a bit unclear. But in 3 dimensions, at least, let me recap what it is that we know already. So the lower dimensional EFT has already been worked out. We start from type 2B and compactify on what is called a co-calibrated G2 structure manifold. These are simply G2 manifolds with curvature. So essentially, the fundamental 3 form doesn't close anymore. And the non-closure or the deviation of these manifolds away from G2 holonomy is captured by these 2 torsion classes. And the upshot is that they have a non-vanishing curvature. They're not really flat anymore. And the curvature can be computed in terms of these torsion classes. What does this mean in the toroidal picture, which is what I will work in mostly today? So when you have a 6 torus or 7 torus, sorry, in this case, you can characterize the fundamental 3 form in terms of Weil bind, right? So what it means to introduce these torsion classes from the point of view of the torus is simply to twist the torus, right? Or for people familiar with flux compactification, we're simply introducing metric fluxes, where I call these tau I, j, k, which are like structure constants of the Lie algebra, the metric fluxes. They satisfy certain constraints. And in principle, you can rewrite now the fundamental 3 form in terms of these twisted Weil bind, right? So a lot of the intuition that you have for the untwisted flat torus sort of goes through. You can write down the fundamental 3 form and discuss orbifolds of this twisted torus as well, which is what we will do. And as I said, these follow certain constraints. This will restrict the kind of manifolds that we can pick. But yeah, this is just a detail. It's not particularly important for us. There has also been related work from people. I'm not doing a good job of being exhaustive in my citations. But the reason is I'm restricting to supersymmetric scale-separated vacua. So there's a lot of literature on finding supersymmetric vacua without scale separation, or non-supersymmetric vacua also with scale separation more recently. But I'm going to restrict really to supersymmetric scale-separated vacua. Okay, excellent. So the upshot of trying to compactify on some G2 structure manifold is to obtain eventually some n equals 1 3-dimensional theory. And also for this, the superpotential is worked out by George, Fortis, and Max and Emelin a few years ago. And this is all we need really to start playing the game that we will play in a moment. But just for completion, let me point out that already the first scale-separated vacua in type 2B, I think supersymmetric ones at least, have been studied and understood in this setting from Vincent. And I think from the Oviedo group, there are also non-supersymmetric scale-separated vacua, which I don't understand quite well. But at least Vincent's analysis is extremely exhaustive. So Vincent goes through the set of nil manifolds that are compatible with the Joyce orbifold and generalizations thereof, and tries to understand whether there are properties like scale separation, integer conformal dimensions, and so on and so forth. So the solutions that I will speak about in a moment are slight generalizations of Vincent's solutions, in the sense that the T-dualities that we will do will take us to a nil manifold from the flat toroidal orbifold, which he does cover, but the flux scalings that we allow are more general. So this is what I think Vincent calls non-homogeneous flux scalings. And this is what allows us to find solutions that are not captured in his analysis. Vincent, please feel free to correct me if I'm wrong at any point, but I think this is the status. Okay, if there are no questions at this point, I can actually start showing you the T-dualities.
Okay. Could I ask one
yes,
quick question?
Please, yes.
In discussing the calibrated G2, like maybe a slide or two back, you're stressing that when you turn on fluxes, you get non-reaching flat backgrounds.
Yes.
Wouldn't you have said the same thing about the model starting a massive 2A, where people start with reaching flat backgrounds?
Okay. Yeah, you're saying like the backreaction of the fluxes, like the Raman fluxes and so on, should have taken me away from Ritchie flat. Yeah, I completely agree. This is we're working like with the stupid smeared analysis where it seems that you can go to arbitrary large volume and dilute the fluxes. Where I would say then, okay, at least as an approximation, you have a solution, but not without smearing. And this is a problem. I'll speak about this problem later as well. I don't have a solution to this problem here either. So let me be honest. Like these are at the same level of those.
Great, thank you.
Okay, perfect. So now let me actually get to what we're trying to do. So the aim is to do naively 3 T-dualities from the massive type 2A setup that George spoke about and that I recapped. And we'll be careful in choosing the directions along which to T-dualize, such that we don't end up with any non-geometric fluxes in the type 2B side. This is a naive application of the map of the Busher rule, which was done very elaborately in the type 2 setting by Shelton, Taylor, and Beck. And as I was saying before, the reason why I introduced you co-calibrated G2 manifolds is for the fact that when we do the 3 T-dualities, our NS and S fluxes actually get rated for metric fluxes. So it's exactly in the framework of co-calibrated G2 structures that we'll end up in when we perform 3 T-dualities on this massive type 2A setup. All right. So let me be a bit more specific. So what happens? The Roman's mass parameter in the massive type 2A side ends up becoming a component of F3 flux in the 2B side. Various components of F4 flux can become F3 or F7 flux. And the NSNS flux, like I was saying, becomes metric fluxes. There's a bit more to this story, right? Okay, as I was saying before, the curvature does not vanish. But what I really want to say is that the source is also in principle transformed. So George showed you like the web of orientofold planes that arise when you have the orbifolds that he chose and the involution that you do on top of that. These also transform under these T-dualities. And if you naively apply the Busher rules, you find a web of O5, O9 planes in the type 2B side. So really we're working with a type 1 setup now after the 3 T-dualities. Now there are several things you should be potentially worried about. So one maybe slightly not so worrying thing is that I do have D5 brains. So you should ask me like, aren't there open string modes that are coming from this and how are you dealing with them? It turns out that this is really just an artifact of the orbifold we picked. We could pick a different orbifold and do away with these O5 planes that have to be cancelled by D5 brains, and the physics has not changed. So the other O5 planes in the O9, D9 are still there. So this is an issue that we can sort of get away with. But there is a more maybe severe issue, which is also there in principle in 4D and for the massive type 2A solutions, which is that you can see from staring at these web of O planes that they do intersect. But once again, this is really a shortcoming of the way we are going about our analysis. I think this is an artifact of the fact that we're working with toroidal or the toroidal orbifold description. At least this is what seems to happen in the 4D case. So Daniel, who I think is also in the audience, did this analysis very carefully for the DGKT CFI vacuum. And what he sees is that if you don't work with the toroidal orbifold picture, instead you blow up the singularities and start with the Calabi-Yau, that you can get away with these intersections. They're not there anymore. The same story could in principle be run for the 3D case, although we are nowhere close to doing this. But at least I'm hopeful that this is possible. All right. So now let's actually start looking at the explicit flux configuration that we're going to dualize. So this will look slightly different from the fluxes that George showed if you were really carefully observing it. And this is thanks to a point that was raised to us by Gonzalo, who's a PhD student at IFT, and Luis, because there's a subtlety about flux quantization which we were not careful about. And that's why this flux configuration looks slightly different from George's, because this is corrected to account for this. I just wanted to show this one here so that it's clear that in principle we have enough freedom of flux configuration to still have a good physical vacuum. Anyway, that point aside, if I apply the rules I told you a couple of slides ago, what I end up with the following configuration. I've slightly generalized this. So in principle, the F7 flux that I get from the F4 flux does not scale the same way as it was scaling before on the type 2A side. And this will allow us to find some more general class of solution. So really what we could have done is just started with the type 2 side or the type 1 side and chosen this flux configuration, which is why I was saying you need not worry about the T-duality if there are any subtleties there. It's really just a guiding principle or an inspiration to understand what ingredients you need on the other side. And one can go and play the game that George was playing in the massive type 2A side and ask what are the critical points of my superpotential such that the superpotential doesn't vanish. There's also the Bianchis that you have to satisfy. These are like tadpole. And again, the Fourier emphasized, we're doing something that should worry you here. We're smearing the orientofole. And this is how we're able to cancel the tadpole. And you can see, doesn't mean much to you, the expressions I'm showing, but essentially you can fix all the moduli in terms of the fluxes. But the more crucial point is that these three fluxes actually remain completely unconstrained after solving the equations and the tadpoles. And this is what will allow us to get the behavior that we're interested in. So I'm, I think, running out of time. So let me get to really the point or the result, which is that there are different scalings of these fluxes, all becoming large with different hierarchies, essentially, that gives rise to different families of solution. For example, actually, before that, I should discuss what I mean by scale separation. Sorry. So what I mean by scale separation really, and what we mean in this whole talk, is that we're able to separate the KK scale from the AdS radius. Right? So I should tell you what I'm using as a proxy for the internal diameter of the manifold. So one thing one can do is just look at the volume of the cycles, right? These are the only dynamical sort of moduli you have in the theory, at least before resolving. And in every solution that I'm saying we find scale separation, this scale is separated from the AdS radius. But in principle, this is not good enough, right? You can complain and ask, why don't you go and solve the Laplacian, find the spectrum of the Laplacian, and then do a more complete and rigorous analysis. And it turns out this is a bit complicated to do. So we wanted to cheat a bit, but to still stay safe, what we did is, since underlying this whole setup is a toroidal orbital fold, we said, okay, we take the separate radii of the one cycles, even though they're not dynamical, and think of this as a more stringent condition to check for scale separation. And so what I really mean when I say we find scale separated vacuums with respect to both these scales, we find a separation for the AdS scale. And I think in principle, what we're doing is not super illegal for the following reason. I think David Andreou and Dimitrios Simpis worked out the spectrum of the Laplacian for nil manifolds, for simple nil manifolds, and ours is an example of a simple nil manifold. And I think at least in the parametric limits, the scalings of the KK, the masses of the KK modes is not in big disagreement with the sort of scaling that I'm choosing here. But if there are objections, please feel free to raise them, of course. So I just wanted to make the point that I think when we say we're finding scale separated vacuum, at least from the supergravity point of view, I think this is a fairly robust statement. Okay, so what are the actual solutions? So when all three of these fluxes become large, grow large with this specific hierarchy, we can recover the solutions that George was finding in the type 2A side. And this should not be surprising because in principle, we went and did 3 T-dualities. So when he has solutions where everything becomes large, where all cycles are becoming large, we should find a solution where these cycles are shrinking. These are not the solutions we're really after, because I would not call these like safe and scale separated solution. But it turns out there's another hierarchy of fluxes one can pick, such that every cycle grows large, you have large volume, scale separation, and decoupling. Not only this, you can also choose a different scale hierarchy between the fluxes as they go to infinity, and find a family of strongly coupled solution. Of course, the type 1 description breaks down, but it turns out there is a S-dual heterotic description, which George and Tim studied last week. And as George pointed out, maybe this paves the way to understand the worldsheet description of these, and maybe settle the debate on scale separated vacuum and string theory. Before I conclude, I want to flash some disclaimers. So first of all, the philosophy of this construction is not to claim that we have a string theory scale separated vacuum, but to rather find candidates that could uplift to string theory solutions. And there are several obstacles that one has to encounter to to actually establish this. One is the smearing of O-planes that Sav brought up, that people have discussed a lot in the literature. I think there's been a lot of progress on this, both in 3D and in 4D in the recent past. That at least when you're far away from the orientable plane, you can try to localize the O-planes and study the back reaction order by order in these 3 parameters. And everything looks consistent. In principle, an inconsistency could have already risen at this level, and so far, at least, we don't find any. I don't think the analysis for our solution is very different from these setups. So I think at least these arguments should go through, but one has to actually go and check this. The other issue was something I also raised, the intersection of forces. This is very closely related to the other problem, which is blow-up modes. These have to just be carried out, I guess. I mean, I don't have any intuition or reasoning to claim that these issues would go away, but these are certainly there if you want to claim that we have a string vacuum. And with that, I think I'll thank you and end there. Maybe just with one finishing line, which is that what we presented to you today was some massive type 2A and type 1 solution, which have the same properties as the DGKT CFI vacua with parametric scale separation. And I think they're at least decent candidates to be uplifted to string theory. Thank you.